All right, so what we're doing here is we are just going to talk about some problems from 5.5. And 5.5 is all about just making substitutions in our integrals. So this video is pretty much just going to be solving some integrals which require u-substitution. So let's evaluate the following integral. I will take x times the square root of 1 minus x squared dx. Now, I think it's pretty clear that this integral is not in a standard form for which we can use. And even if I distribute this x into the radical, it still would not be in the form of an integral we could directly evaluate. So we're going to make the following substitution. Let u be everything inside of that radical. Then the differential of u is going to be the derivative of this function, so just a negative 2x, accompanied with the differential of x. So if I say divide both sides by a negative 2, then negative du over 2 is equal to an x dx. And now we can replace the variables we have in this integral. So first things first, I'm going to rewrite the integral. And then I'm going to rearrange it so that it's a bit more explicit how things will get replaced. Notice that over here I have this du. And notice that underneath the radical, I just have u. Well, not du, but a negative du over 2 to be specific. You got to be careful in these problems by making sure that you're taking care of all the coefficients that you had to either multiply or divide by in finding your expression for this function times the differential of x in terms of the differential of u. All right, great. Well, now that we have that in mind, we can now make the replacement in terms of u. So first I have the square root of u, and then as we wrote over here, we have a negative du over 2. But all these constants, by the rules of integration, I can just factor out of the integral. So this is like a negative 1/2 square root of u du. All that was just me pulling out the constant negative 1/2. Because all negative du over 2 is a negative 1/2 times du. And now we're in the form where we can just directly evaluate this integral. I think that a lot of people don't remember what the integral of the square root of u is, but if I instead write it as u to the 1/2 power, I think that everybody remembers what the rule for u to the nth power is. So first things first is that coefficient is going to tag along. And in here, I'm going to place the antiderivative we get here. So I add 1 to this power, and that's our new exponent. And we'll have to divide by this new exponent as well. And remember, because it's an indefinite integral, we're talking about the most general antiderivative here. So we have to add the constant c, because a specific antiderivative could be this function plus any given constant, since it'll go away when we derive. Now, we just note that 1/2 plus 1 is the same thing as 3/2. So this is like 1 over 3/2. And this is like u to the 3/2. But if I just flip the reciprocal, this is now a negative 1/2. I get a 2/3 u to the 3/2 plus c. So finally, when I do my multiplication here, what I'm going to get is a negative 1/3 u to the 3/2 plus c. But we're not done here. If this were a definite integral, then I could just take limits of integration after I found my new limits and call it a day. But because it's an indefinite integral, we have to get it back in terms of x. So if we sort of look back what we had up here, we saw that u was equal to a 1 minus x squared. So I'm just going to replace this u with a 1 minus x squared. And now I have a nice negative 1/3 multiplied by a 1 minus x squared to the 3/2 power plus c. Now, obviously that's not where we start. Let's see how u-substitution can make integration easier on us, even if it's a function that we could technically integrate using our rules. So together we are going to evaluate the following indefinite integral. Say I take a 1 minus 2x to the 9th power. Then technically, we could integrate this using our standard rules. It's just that I would have to multiply 1 minus 2x 9 times. And I think that most of us just would not prefer to expand out this polynomial and deal with all the powers of x we're going to get. Well, that's fine. Instead, let's make the following substitution. Let's let u be 1 minus 2x, so everything in this parentheses. Then the differential of u is going to be equal to the derivative of this function with respect to x. So that's just a negative 2. And we multiply by the differential of x. So if we divide, we actually find that once more we have a negative du over 2 equal to dx. So I take the original integral that was in terms of x, and I just start replacing. Now, this term here is u, so it's like u to the 9th power. And dx is just a negative du over 2. So once more, I actually have this 1/2, the integral of u to the 9th power du. So, interesting little thing. We got the same coefficient as last time. But obviously we're not going to get the same end result, right? So, continuing our integration here. If it's u to the 9th, then that just means that my new power is 10. I add 1 to 9. And I divide out by my new power, that's just 10 as well. And of course I have that constant. Now, multiply these fractions and we get a negative 1 over 20 u to the 10th plus a c. If it's an indefinite integral, you make sure to never forget that plus c. You want to make sure that you get the most general result that you can. Now, at this point, it's just replacement. So the negative 1 over 20 comes along, but now instead of having u here, I put the 1 minus 2x, and my new power is 10, plus the c. We call it a day. So even though we could have just taken this integral and expanded out the terms, why do that to ourselves when we can just make a simple substitution and not have to do all that extra algebra and get bogged down with those waters? All right, great. Now, we've been sticking to some very nice functions. Everybody knows how to work with their polynomials, I think, or at the very minimum, they understand them a lot more than their trig functions, even if they can't be perfect with them. Now we're going to get into some trigonometric functions as our integrands. So let's evaluate the following indefinite integral. I'm going to take a secant squared of theta, a tangent cubed of theta, and integrate it with respect to theta. Okay, well, I think it's pretty clear that this isn't really in our integral table. And even if we sort of try to play around with, the terms that we have here, get it in terms of sine and cosine, it's not as though we could get it into a form where it's just a standard trig function. So what that means for us is that we have to make a substitution. Now these are a bit tricky, but you have to sort of look for a derivative here. So you got to think about what your standard derivatives for the trig functions are. If you take the derivative of sine, you get cosine. If you take the derivative of cosine, you get a negative sine. But I don't have sine and cosine in here this time. I have tangent, I have secant. So let's think about what the derivatives of these trigonometric functions are. Well, if I take the derivative of just tangent, what happens is that I get a nice secant squared theta. And if I take the derivative of secant, then I get a secant times a tangent. Oh, no bar there. All right. Now, looking at this integral we have here, I think it's pretty clear that we have one of these derivatives right away. Namely, I got the secant squared. So I'm going to try and let u be tangent first and see if that gives us any results here. So let's let u be equal to tangent. Then du is equal to secant squared theta d theta. Well, turns out I actually have that right there in our integral. So the integral of secant squared theta times tangent cubed theta d theta in terms of u now is actually u cubed du. I didn't even have to divide by a constant this time or multiply by anything. The differential of u was actually right there in the integral. Now, this is just a standard integral in our table. So if I take the integral of u cubed and integrate it with respect to u, I get a u to the fourth, and I divide by that new power, that's also u to the fourth. It's going to be over 4. And of course, we have to account for that c. Now we just replace. So u was tangent theta. To get this back into terms of theta, it'll be tangent to the fourth power over 4 plus c. If you prefer the notation that they do here, where you put the power between the word and your variable, then you can write it as tangent to the fourth power of theta over 4 plus c. Me, I personally just like the brackets a bit more. I know it's a bit clunkier, but I feel like it's a bit more explicit. But I think that this is also easy to read as well. I just like being a bit rigorous. All right, great. Now, so far we've been talking about indefinite integrals. What I want to talk about now are some definite integrals. Seeing what we can do with those. So now I'm going to evaluate something that actually has limits of integration. Let's see, we did a trig function. We did some polynomials. Let's do something involving an exponential. So now I'll take the integral from 0 to 1 of x times e to the negative x squared dx. Now I think we all know that right off the bat, we're going to have to make a substitution here because this is not in our standard integral table. But if I let u be equal to x squared, then I think it's clear what the substitution, then I think it's clear what this integral will rewrite as. But I want to make it clear that you can also just take u to be exactly negative x squared. My advice is that in the beginning, you should be taking the entire power or the entire thing in your parentheses rather than trying to do any shortcuts. Once you've made it to calculus 2, calculus 3, once you've gotten past this section, then if you're fine just saying, okay, well, let u be x squared, and then you'll get something in the form of like an e to a negative u and such, then fine. You know, if you're able to just easily do e to the negative x versus e to the x, more power to you. But until you're there at that point, for now, I would just say, take the entire power to be your substitution. So if I let negative x squared be u, then the differential of u is going to be a negative 2x dx. So once more, divide by a negative 2, and I have a negative du over 2 equaling x dx. Well, great. Now we can actually make the replacement. So if I replace things and get them in terms of u, now I have a e to the u, and I have a negative du over 2. The problem here is that what are my limits of integration? Are they still 0 and 1? Well, no. These were whenever we had it in terms of x. So one method that you can do is that you can make sure that you just keep track of these limits and keep them in terms of x. Then replace back u to be in terms of x and plug those in. Or you can find new limits of integration. So once more, I'm going to pull out these factors first. This constant first, the coefficient. And just make the inside a standard integral. What I'm going to do now is I'm going to replace these limits of integration in terms of u. So when x equals 0, u up here is equal to a negative 0 squared, which is equal to a nice 0 still. Okay, well, great. The limit of integration did not change. When x equals 1, u is equal to a negative 1 squared. Well, that's actually just a negative 1, because the square is only applying to the things that we have in our parentheses here. Well, that means that the new limit of integration up here, our upper limit, is negative 1. So continuing from this integral, negative 1/2, the integral of eu du, with our limits of integration with respect to x, is now the integral from 0 to negative 1 of eu du. Now we have two options. One is that I can just take the integral, evaluate, and then multiply by this negative 1/2 later. Or I can recognize that I have a negative here, and I want to rearrange these limits of integration. So one thing that I can do is that if I multiply this negative and just leave the 1/2 on the outside, then it flips the order of integration. So instead of having the negative here, I can remove it, but the cost of that is that I flip my order of integration. Otherwise, the integral remains unchanged. The function is still the same. The only thing that changes is that your order of integration gets flipped. Okay, well, great. Now that we flipped it, we can just directly integrate. So if I take eu du and I take this indefinite integral, well, I would just get eu. And now I have to keep track of my limits of integration over here. Just replacing it, I get a 1/2 e to the 0 minus 1/2 e to the negative 1. E to the 0 is 1. And then e to the negative 1 is just the same thing as 1 over e. And there we have it. That's your final answer. You do not need to give an indecimal approximation. In fact, you really should not. Keep things as exact as you can. Now, what I said before is that if you did not flip the order of integrations and you just sort of directly evaluated, that you get the same result. So I'm going to leave it to you to check the following. Check that if I had kept the negative on the outside and just done the integration immediately, that this would still be equal to 1/2 minus 1 over 2e. I really like these exponential questions, to be honest. You know, I like exponents. I'm an exponential type of guy, honestly. Now, let's do something that might scare some of y'all. So, some of these integrals are not necessarily easy to solve. And some of them you just can't really solve using elementary integration techniques. So instead, you solve them in terms of symmetry. So now if I take the definite integral from negative pi over 3 to a positive pi over 3 of x to the fourth times a sine of x dx, then we want to evaluate this. Well, before you try to do any u-substitution, if I have something in the form of negative a to positive a, then what should immediately jump out to you is to check for symmetry. These problems are all about just making sure that you can quickly evaluate whether a function is symmetric about the origin or the y-axis, i.e., is that function even or odd? So let's let f of x be equal to the function in our integral. We're going to determine the symmetry of this integrand. So if I take a negative x and plug it in everywhere I see x, then what goes here now is a negative x to the fourth power times a sine of a negative x. Now, if I have a negative here, we can treat this as negative 1 to the fourth power times x to the fourth power but then a negative 1 to a even power is going to be a positive 1. And this x to the 4 is just x to the fourth. Now, this is just something that you have to remember. Sine is an odd function. So that negative there, it just pops out of the function. I'll just bring that back to the front. And we have the same thing as negative f of x. So what you should recognize here is that if f at negative x is the same thing as negative f of x, then we have that f is odd. Thus, by the rules of symmetry, if I take the integral from negative pi over 3 to positive pi over 3 of x to the fourth times sine of x, it's just equal to 0. And we have to be pretty thankful that that's the case for us, because otherwise we could not evaluate this integral. Since there isn't really a substitution we could do here that would let that happen. All right. Great. I think that we can talk about maybe another integral. Let's see what we have here. I guess I haven't really talked about the inverse trigs. So let's do a pretty basic one, the arctangent. So let us evaluate the integral of arctangent of x squared over x squared plus 1. Well, first things first is that whatever is here in parentheses is usually the first substitution that you make. But the goal eventually is that you get good enough to immediately spot derivatives of functions in your integral. So you don't always want to say, okay, well, it's on the bottom, I'll substitute that. It's on the top, I'll substitute that. You don't want to fall into that habit. What you really want to get good with is noticing that you have a function here and you have its derivative somewhere else in the integral. So if we take a nice arctangent of x to be u, then what we should recall is that the derivative of arctangent is 1 over 1 plus x squared. And of course we have that dx here since we're finding the differential of u. Well, if this is confusing to you, you could also rewrite this as x squared plus 1. Right? It's just addition. Nothing wrong with that. But we have exactly that in our integral. So let's make that substitution together. We have an arctangent of x, and I'm squaring that function. I divide by this x squared plus 1. To make things a bit more explicit, we can always rewrite this as arctangent of x squared times 1 over x squared plus 1. And then getting it in terms of u, this is like u squared du. This is just a direct integral evaluation now. I get a nice u cubed over 3 plus c. Then getting it back in terms of x, we just have a nice arctangent of x, raise it to the third power, over 3 plus c. And pretty much all of the integrals are going to be like this, where the end goal here is to just recognize your substitution that you need to make, get it in terms of your new variable, and then it's just direct integration using the rules that we've learned in previous sections. Sometimes we have to invoke the fundamental theorem of calculus. Other times, it's just finding a general antiderivative. And some questions are actually made even easier if we just use a little bit of symmetry. I think that instead of going with this last one, just because I only did one definite integral, I think I'll leave y'all with one more definite integral. So let's grab a bit more paper here. All right. So let's try something a little odd, right? All right, let's take the integral from e to e to the 4th power of dx over x times the square root of the natural logarithm of x. For those of you who may be a bit confused on how to think about this. Well, first things first is that I'm just going to note that you can always think of this as instead 1 over x, the square root of ln x dx. If you don't like the dx being on top, you can always just move it to the right. There's nothing wrong with that. So if you read it better like this than this, that's fine. The main goal here is to figure out what derivative we have here. Well, maybe it would help if we instead rewrote the integral like this. Maybe a 1 over x times a 1 over the square root of ln x dx. In fact, maybe it would be even better if we switch these two around. And I got my square root of ln x here, and my 1 over x dx over here. So what do you think I'm going to let u be in my substitution? I would let it be that function, ln of x. Because what is the derivative of the natural log? 1 over x. So the differential of u is just 1 over x dx. I have that immediately. Now we have to be a little bit careful because this is a definite integral. I'm going to find my limits of integration in terms of u. So when x equals e, we have u being equal to the natural logarithm of e. That should be an identity that's clear as day to you at this point. That's just one. If it's something you forget, you should know how to plug this into your calculator to double check. But I'm hoping that at this point, you're pretty solid in this identity. When x is equal to e to the 4th power, we have u being equal to ln of e to the 4th power. This one may not be as obvious, but if you remember that powers in your logarithm come down as coefficients, then it's 4 times ln of e. That's just 4. So now that we have our new limits of integration, we have all the things we need to get this integral, which is in terms of x, into terms of u. So just looking over here, this is like a 1 over the square root of u. And this term, 1 over x times dx, is our du. Our new limits of integration now are 1 and 4. And now this is just a direct integral evaluation. If you don't believe me, let's think about how we can rewrite this function. Well, 1 over the square root of u is the same thing as u to the negative power 1/2. So I think we all agree that the square root of u is the same thing as u to the 1/2 power. If I take 1 over that, it makes the power negative. So I hope we're all okay with this rewriting. Once you're comfortable with that rewriting, then it is indeed just a simple integral evaluation. We have a negative 1/2 plus a 1 as our new exponent. It's also going to be a new denominator for us. And of course, we're still taking the limits of integration 1 and 4. Now, Negative 1/2 plus 1 is just a 1/2. So over here I have a 1 over 1/2. This will be a 2, and then I'm just going to replace back the square root. Now, I take my limits of integration. And I can either factor out the 2 and take my limits, or I can distribute it to both terms. This time, I'm going to factor it out because I distributed last time. Let's take the 2 out, and then I have the square root of 4 minus the square root of 1. The square root of 4 is just 2. The square root of 1 is just 1. This is going to be a 2 times a 1, which is just a nice 2. And I think that that can conclude just a plethora of examples that we'll be discussing in this chapter that might help you prepare for our upcoming tests and any future work that we might have where you need to invoke the rules of substitution.